Although today the sun is shining bright over Stevensville, Montana, thermometers are reading minus 20 degrees. That's almost minus 30 degrees Celsius. That's cold enough to freeze water in mid-wave. As the wind blew the water, it created waves. The cold snap came in almost instantly, freezing the water in its place. Strong winds created snow drifts that could be small and insignificant, or almost as tall as a full-grown man. The wind and snow worked together to transform entire landscapes. The wind was so strong that it blew snow and created drifts inside of barns and sheds, as the wind forced the snow through the tiny cracks in the walls and doors. The amazing part about this is not so much the cold weather, but the fact that it happened almost overnight.
So what exactly causes these sudden cold snaps? Well, a team called the National Center for Atmospheric Research, or NCAR, may have our answer. NCAR used a sophisticated Earth system model to analyze the sudden stratospheric warming that occurred on January 5th, 2021, and its potential impacts, using a new method to assess causality. They found that while the subsequent weather did indeed match the expected pattern, the sudden stratospheric warming itself was not likely the cause. The mechanisms for how these layers of the atmosphere interact are probably more sophisticated than we're giving them credit for, and that's important in making better forecast models, said NCAR scientist Nicholas Davis, who led the study. Once you know the mechanism, you can model it better. But back to the question at hand. What causes these sudden cold snaps? Occasionally, the polar vortex is disrupted by planetary scale waves, which propagate upward towards the troposphere, the lowest layer of the atmosphere. When the planetary scale waves break, they warm the vortex, which can weaken it and cause it to displace and split in two. This event is called stratospheric warming. And the month afterward is usually warmer than normal in Canada, Alaska, and the Middle East, and colder than normal in Siberia, with more frequent cold air outbreaks in Europe and the United States. For the new study, the researchers dove into the connections between the stratosphere and the troposphere, using the NCAR-based Community Earth System Model version 2, or SCSM2, configured with an atmospheric component called the WHOLE. Atmospheric Community Climate Model, WACCM. They performed supercomputer-based algorithms at the NCAR Wyoming Supercomputing Center. To start, the team kicked off the model using the atmospheric conditions present in both the stratosphere and the troposphere on January 4th, 2021, the day before the sudden stratospheric warming took place. This is standard forecast. Did an excellent job of capturing the weather that accurately occurred over the following 4 weeks. Then the team ran 3 more forecasts. In one of the forecasts, the troposphere was scrambled, meaning the conditions in the troposphere did not match the actual weather observation from January 4th, 2021. In a second forecast, the stratosphere was scrambled, which removed the sudden stratospheric warming from the forecast. The scrambling experiments showed that the ideal state of the stratosphere had no impact on the weather in the 2 weeks after the sudden stratospheric warming, and only a minor impact nearly 1 month later. I think everyone imagined that a pinball is shot up from the troposphere and hits the polar vortex and breaks it apart, Davis said. And then another pinball shoots back down and changes the weather. But this study shows that it's not so simple. I think it's possible that the events of the troposphere and the stratosphere are feeding back in one another and reinforcing what's happening.